We live in an age of miracles, but we've gotten used to them. Artificial intelligence today is performing feats that just a few years ago felt like pure science fiction. It composes hauntingly beautiful music. It writes elegant and complex computer code. It's even mastered the ancient game of Go, a game of such profound strategic depth that for decades it was considered untouchable by machines. An AI grandmaster can now routinely defeat the world's best human players. But behind this spectacle of superhuman intelligence lies a shocking, hidden cost, a secret that is rapidly escalating into one of the most urgent and unsettling technological crises of our time. And it begins with a single glaring anomaly. Picture that AI grandmaster deep in digital thought, contemplating its next move as it churns through billions of possibilities. Its powerful processors are burning through tens of thousands of watts of electricity. Now picture its human opponent across the board. Her brain, a dense and mysterious network of cells, is running the exact same complex strategies, navigating the same labyrinth of possibilities on just 20 watts of power. Let that sink in. 20 watts. That is barely enough to power a dim light bulb. This isn't a small difference in efficiency. It's a colossal, unignorable gap that screams a fundamental truth. We are building intelligence, but we're building it on a foundation that is profoundly, deeply wrong. And this problem gets exponentially worse when you zoom out. A single massive data center built to train the latest AI models can consume as much electricity as a small city. The International Energy Agency predicts that by 2030, data centers could consume double the electricity they use today. This explosive growth is creating an unprecedented energy crisis, putting an immense strain on our power grids and jeopardizing our climate goals. Big tech companies that once made ambitious climate pledges are now seeing their emissions spike, driven almost entirely by their relentless push into AI. Our current path, the one where we make AI smarter by simply feeding it more and more raw power, is becoming utterly unsustainable. It is a path that leads directly to an energy crisis and an environmental disaster. This brings us to the central, powerful question that will drive our entire journey. It's a question that is forcing a desperate scramble within the entire technology industry. If we cannot just keep throwing more power at the problem, how do we continue the extraordinary advance of artificial intelligence without bankrupting our planet? What is the secret to building a mind that is not only powerful, but also wise in its use of energy? To answer that, we must first understand the deceptively simple idea that got us here in the first place, an idea that for 50 years was the engine of all technological progress. For the last half century, the world of technology has been ruled by a single, elegant, and incredibly powerful idea. It was more than a theory. It was a promise, a prophecy that became a self-fulfilling engine of progress. It was called Moore's Law. It all started in 1965 with a quiet engineer named Gordon Moore, who would later co-found Intel. In an article for a trade journal, he noted a fascinating trend: the number of components, transistors and resistors, that you could cram onto a silicon chip was doubling roughly every year. He predicted this trend would continue, and though he later revised the doubling period to every 2 years, his prediction held with the reliability of clockwork for 5 decades. Moore's Law became the heartbeat of the digital revolution. It was the simple, powerful promise that our computers would just keep getting smaller, faster, and cheaper, year after year after year. Every challenge in computing, from the grandest to the most mundane, had a single, unified answer. Just wait. If a problem was too hard today, just wait 2 years. The chips would be twice as powerful and the problem would become solvable. This relentless, predictable march of progress is what took us from giant, room-sized mainframes to the supercomputer you now hold in the palm of your hand. It was the hero of our story, the established wisdom that carried us into the modern age. So, when the incredible energy demands of AI started to become a pressing concern, the prevailing logic, shaped by 50 years of experience, was to fall back on what had always worked. The problem of AI, it was assumed, was simply a problem of brute computational force. To achieve greater intelligence, we just needed more powerful hardware. The answer, therefore, must be to apply Moore's law. Build bigger data centers. Engineer more powerful GPUs. Just as we had always done, we would simply engineer our way out of the problem, assuming that raw power was the only path to smarter AI. This mindset was so deeply ingrained that it felt less like a strategy and more like a law of nature. The entire industry bought into this logic. It was comfortable, familiar, and it had a half-century track record of delivering miracles on a reliable schedule. For a time, it created a strong sense of false security. The AI energy problem was just a temporary hurdle, a speed bump on the inevitable road of exponential progress. The answer was simple. Trust in the chips, trust in the engineers, trust in Moore's law. But this perfect story was perhaps a little too perfect, because while the world was looking to the familiar hero for salvation, a series of strange and troubling clues were beginning to emerge. Cracks in the very foundation of our computational world that suggested this time the old hero was not coming to save us. The perfect, elegant story of Moore's law began to fray at the edges, slowly at first, and then with an alarming, accelerating cascade of discoveries. The sense of security it had provided for so long started to give way to a frustrating, deepening mystery. The clues were not just isolated facts, they were systematic attacks on the very pillars of the established wisdom. The first and most obvious crack was the end of Moore's law itself. The decades-long trend of chips getting exponentially more powerful began to slam into a hard physical wall. For 50 years, we had made transistors smaller and smaller, cramming more of them onto a single slice of silicon. But that incredible shrinking act was approaching its physical limit. Transistors today are measured on an atomic scale. The smallest are barely wider than a strand of DNA. You simply can't shrink them forever. The laws of physics were drawing a line in the sand, making it clear that the easiest way to get more power, just cramming more stuff in, was coming to an end. Since around 2010, semiconductor advancement has noticeably slowed, falling off the pace that Moore's law had predicted for decades. The old promise of free biennial doublings in computational power was broken. Relying on it was now leading us into a computational dead end. But the bigger problem, the true villain of our story, was not a limitation of physics, but a fundamental flaw in our design. It's an architectural inefficiency baked into nearly every computer on Earth, from the cheapest laptop to the most powerful supercomputer. It's called the von Neumann bottleneck. Named after the brilliant mathematician John von Neumann, this architecture is the basic blueprint for all modern computers. It has two separate places for two crucial functions: the processor, which is the brain that does the thinking, and the memory, which is where data and instructions are stored. This separation means the data is constantly being shuttled back and forth between the processor and memory over a shared pathway called a bus. This creates a massive, perpetual traffic jam. No matter how fast your processor is, it is constantly forced to sit idle, waiting for data to arrive from memory. It's like having a brilliant chef who has to run down the street to a separate warehouse for every single ingredient needed for a recipe. It is wildly, ridiculously inefficient, and this constant shuttling of data is not just slow, it wastes an enormous amount of energy. In fact, the movement of data can be the most energy-intensive aspect of high-performance computing. The physical act of sending electrical signals across wires to move data consumes power with every transfer. When you consider that modern systems perform billions of these operations per second, the cumulative energy waste becomes immense. For decades, we tried to solve this problem with brute force. Faster buses, clever caching techniques, but these were just bandages. They didn't fix the fundamental design flaw that was wasting so much power. This bottleneck was the second and much deeper crack in our established wisdom. It meant that even if Moore's law hadn't ended, just making faster chips wouldn't solve the energy crisis. We would just be building faster engines to sit in the same traffic jam. And that brings us to the final, and most damning piece of evidence, the anomaly that started it all, now reframed as an unsolvable paradox, the brain's supercomputer paradox. Remember the 20-watt brain and the multi-megawatt supercomputer? In the light of the von Neumann bottleneck, this wasn't just a curiosity anymore. It was the single biggest clue that we were on the wrong computational path. The brain doesn't have a von Neumann bottleneck. In its architecture, memory and processing are woven together. Neurons and synapses, the biological equivalent of processors and memory, are fundamentally integrated. There is no separation, no traffic jam. This huge, glaring anomaly stared the entire field in the face. Our most powerful machines, the pinnacle of 50 years of engineering, were consuming 1,000,000 times more power to perform tasks the brain does with the energy of a dim light bulb. The old story was now riddled with holes. Moore's law was ending, the very architecture of our computers was fundamentally inefficient, and the living proof of a better way was sitting inside our own heads, quietly mocking our brute force approach. The weight of things that just didn't add up was becoming overwhelming. The established wisdom was on the verge of collapse, leaving us all demanding a new answer. The collapse of an old idea is always unsettling, but it is also the necessary prelude to a breakthrough. With the trusted path of Moore's law turning into a dead end, and the architecture of our machines revealed as profoundly flawed, the world of computing was primed for a revolution. The stunning breakthrough that would unlock the mystery didn't come from a new engineering diagram or a more clever chip design. It came from a radical shift in perspective. The solution wasn't to build a better machine, it was to finally understand the one that biology had already perfected. The turning point was the moment we stopped looking at the brain as a mysterious, magical object and started seeing it as the ultimate computer, a machine forged not in a sterile lab, but in the chaotic, competitive, and ruthlessly efficient crucible of Darwinian evolution. Over billions of years of trial and error, nature had already solved the problem of intelligence, and it solved it not with overwhelming power, but with radical, breathtaking efficiency. That was the clue. That was the new lens through which to see the problem. We had been trying to win a race by building a bigger gas-guzzling engine, while nature had designed a perfectly aerodynamic frame. This paradigm shift marks a move from Moore's law to what we might call Darwin's law. Instead of pursuing more power and faster clocks through conventional engineering, the new goal is radical efficiency inspired by biology's smarter, more elegant architecture. This is not just a poetic idea, it is a concrete engineering discipline with a name: neuromorphic computing. Neuromorphic computing is a total revolution in how we design chips. The goal is simple and profound: build a computer that works like the brain. This isn't about creating a wet biological computer. It's about mimicking the brain's architecture and principles in silicon. It boils down to two brilliantly clever ideas that directly address the flaws we uncovered. First, neuromorphic chips are built to eliminate the von Neumann bottleneck. They get rid of that inefficient separation between the processor and memory. Instead, the computation and the memory are woven together in a dense network of artificial neurons and synapses right there on the chip. This is called in-memory computing, and it completely gets rid of that wasteful data traffic jam. Second, these chips are event-driven. A traditional computer chip is like an engine that's running at full tilt all the time, whether it's doing heavy work or just waiting for your next keystroke. It's a massive waste of energy. A neuromorphic chip, however, operates on the principle of spikes. Just like a real neuron, a circuit only powers up and performs a computation when it receives a signal, a spike, from another neuron. If it doesn't receive a spike, it doesn't expend energy. It just waits to be activated. This event-driven approach, where information is transmitted in discrete spikes rather than continuous values, is the secret to the brain's incredible low-power operation. With this new understanding, all the jumbled pieces from the previous chapter suddenly snap into a coherent picture. The inefficiency of our old computers is no longer a mystery. It's a direct consequence of a flawed architecture. The brain's incredible efficiency is no longer a paradox. It's the result of a superior design. The energy crisis of AI is not an unsolvable destiny. It's a problem we created, and a problem we can now solve by finally learning the right lessons. The transition from theoretical elegance to tangible reality is happening not in the distant future, but in the humming clean rooms and research labs of today. This is no longer a conversation about what could be. It is a demonstration of what now is. At Intel, the Lowy 2 research chip, a silicon wafer packed with up to 1 million artificial neurons, is the engine behind astonishing experiments. It is giving robotic arms a sense of touch via neuromorphic skins and granting machines an electronic nose for advanced olfactory sensing, all while operating on a tiny fraction of the power of its conventional counterparts. This technology has scaled into massive systems like Hala Point, which harnesses 1,152 Lowy 2 processors. Now operational at Sandia National Laboratories, it is tackling city-scale computing problems in logistics and infrastructure management, proving that brain-inspired computing is ready for real-world complexity. Meanwhile, IBM's North Pole chip represents another monumental leap. By weaving memory and processing together on a single die, it obliterates the old von Neumann bottleneck, allowing it to perform complex image recognition tasks 22 times faster and with 25 times less energy than chips with traditional architectures. These are not incremental improvements. They are tectonic shifts in performance and efficiency. These new machines are built upon a foundation of exotic, futuristic-sounding technologies. Researchers are mastering the use of memristors, components that remember the flow of electricity passing through them, making them a near-perfect analog for the brain's plastic synapses. Others are pioneering spintronics to create circuits that can harness randomness and compute with breathtaking efficiency, much like a biological brain. The consequence of this hardware revolution is the liberation of artificial intelligence. For decades, true AI has been shackled to the power grid, a prisoner of the cloud. Neuromorphic computing cuts that chain, unleashing powerful, real-time intelligence at the edge. We are on the cusp of a world with autonomous drones that can navigate a dense forest without a connection to a server, or tiny medical implants that can monitor biosignals for the earliest signs of disease and even help regenerate tissue, all running on the faintest trickle of power. This is the dawn of a new machine, one that allows us to weave intelligence into the very fabric of our world, sustainably and ubiquitously, far from the insatiable hunger of the server farm. The journey had come full circle, ending at its source. The brain was the answer, the undisputed masterpiece of computation. It is the product of a billion-year research and development program run by evolution, a computer so radically efficient that our most advanced supercomputers seem like clumsy, wasteful toys in comparison. To finally replicate its architecture was to reach the end of the quest. Or is it? A masterpiece is always defined by the medium it is created in. A sculptor is limited by their stone. The brain is limited by its biology. For all its phenomenal power, it is a machine made of flesh and salt. Its thoughts are shackled to the pace of life itself, the physical time it takes for an ion to push through a cellular membrane, for a chemical to drift across a synaptic gap. It is the most brilliant machine imaginable, but it is a machine built to operate at the speed of chemistry. This was not a flaw in the design, but an accepted limitation of the material. But what if it didn't have to be? What if we could take this perfect architecture, honed over a billion years of evolution, and give it a body that biology could never build? The answer lay in finding a messenger with no mass, no friction, that traveled at the immutable speed limit of the universe itself. What if we could build a brain that thinks with light, This is no longer a hypothetical. At Tsinghua University, the Tai Chi photonic chip performed complex AI tasks while consuming over 1,000 times less energy than a top-tier commercial GPU. An MIT processor now executes neural network calculations in less than half a nanosecond, at the literal speed of light. Herein lies the truly mind-bending revelation. The most profound lesson wasn't simply how to replicate the brain. It was the accidental discovery that the idea of the brain, its very architecture, to be translated into a medium that biology in all its genius could never access. The ultimate question is no longer about matching the brain, but about what becomes of a mind that is finally given a universe in which to think. For all of human history, our greatest inventions have been reflections of our ambition, not our biology. The lever, the engine, the rocket, these were tools born of brute force, designed to conquer the external world of physics. We built our intelligent machines in that same image, with the logic of a blacksmith, always seeking a bigger hammer, a hotter forge. The solution was always more power, more force, more speed. The final frontier, we assumed, was out there, in the realm of bigger data centers and faster clock speeds. How beautifully ironic, then, that the key to unlocking the future of intelligence required us to abandon that entire philosophy. The great breakthrough was not a final heroic push outward, but a quiet, humble journey inward. The answer was not in the cosmos, but in the silent 3-pound universe between our ears. And so began the great pilgrimage back to the source. The journey wasn't from ignorance to enlightenment, but from the complex back to the elegant, from the engineered back to the evolved. For half a century, we poured our genius into perfecting the chip, bending physics to our will, only to discover its most profound and efficient blueprint was hidden in the evolutionary legacy of the chimp. The very ancestor whose primitive brain we sought to transcend held the architectural secrets we so desperately needed. This realization changes everything. We are no longer merely building a better calculator. By mimicking the brain's architecture, its integrated memory, its event-driven spikes, its radical efficiency, we are doing something far more profound. We are instilling a ghost in the silicon, the ghost of our own cognition, the ancient, energy-sipping wisdom of the evolved mind. Our old machines were alien constructions. We gave them commands. These new machines are reflections. We are giving them a piece of ourselves. The ultimate paradigm shift is this. Our most monumental act of artificial creation is the most deeply natural thing we have ever built. We set out to build a god, and in the end, we held up a mirror.